All right, we'll get started. Okay. Just to go over what we saw last class, there was an interface between a dielectric and an ideal conductor. Okay. And we have used the same coordinate system as what we had used for dielectric interfaces. There is an electromagnetic wave being launched, right? This is a plane wave. It's being launched to the interface. And in this case, since fields don't exist inside of an ideal conductor, you don't have any transmission coefficient to be calculated. So we attempted to calculate the reflection coefficient. We made an assumption that the electric field does not flip its sign and the magnetic field flips its signs in order to form the right-handed triad. Okay. And we proceeded to write down the expressions for the incident fields, which was identical to the case when you had the dielectric interface, right. Once we wrote that down, we wrote down the expressions for the reflected field in the way that we have assumed, right, and we applied some boundary conditions on the interface. Okay. So tangential components of E field continuous, normal components of H fields continuous, right, and once we did that, we were able to obtain that the ER naught or the reflected electric field is going to be flipped in sign, all right, with respect to EI naught. So even though we made an assumption that the electric fields are pointing in the same direction, the calculation reveals that compared to the direction that we have assumed, the electric field actually flips its direction, right. So one of the things to remember is that the E field will flip its direction by 180 degrees when it hits a hard metal ideal conductor interface, right, from a dielectric. So the reflection coefficient can be now written as 1 at an angle of 180 degrees. The equivalent condition for the transmission line was the case of a short circuit, right, where you had voltage reflection coefficient to be equal to -1, right. And we proceeded to write down the total fields in medium number 1 if there is reflection on the interface. And once we finished writing these expressions, we wrote a simple computer program, all right, where we were able to see standing waves in the z direction, all right, and a traveling wave in the x direction, right. We had done it for one of the angles, but you could change the program to use any theta I and you would be getting different values of standing wave, different standing wave patterns depending upon the variables that you are using, right. So now we are going to extend the same concept but a little bit further, right. So I am going to start by writing down the expression for the total field, electric field that we had the prior class, all right. Okay. So as electric field y direction, right. I think we are using the usual notation. So this was my total electric field in medium number 1. Okay. Now let us look at this a little bit more closely and try to see what else can we infer from this, right. Well, the first thing is that the zeros of the electric field, okay, are going to be present corresponding to the term here, right. So I have a sign beta 1 z cos theta I over here. As z changes, beta 1 is a constant for a given medium. Suppose you say that in your problem set that theta I is fixed, angle of incidence is fixed, then depending upon the distance you move away from that conductor, you are going to be having some zeros and these are going to be periodic. Okay. So the zeros of the electric field can be located, right, right. So you can have beta 1 z cos theta I, okay, it's going to be equal to some m pi. This is the argument of the sinusoid, right. Whenever it is going to be equal to m pi, you are going to be having zeros along the z direction. Okay. So, now that we know where the zeros would be, okay, we can also directly say at which positions z you will be having zeros of the electric field, right. So, you can always write this down as m pi by beta 1 cos theta I. If you want to make it little bit more intuitive, you can always write down beta 1 to be equal to 2 pi by lambda 1, where lambda 1 is the wavelength in the medium, and if you substitute for beta 1 over here, right, you will be having m lambda 1 by 2 cos theta I. Okay. This is the location at which your electric fields will completely vanish. Okay. What does this mean, right? So, if we go back to the configuration that we have drawn, right, if we travel in this case along the negative z direction, right. So, if we travel away from this format, right, there are fixed places where the electric field is going to be 0. Okay. Now, electric field equal to 0 can be interpreted in multiple ways, but we will look at it in a simple case from the example that we have taken itself. We know that inside an ideal conductor there are no fields, all right, and the electric field is equal to 0, right. In this case the electric field is tangential, right. So, that means that your boundary condition that needs to be satisfied, right, is E1 tan is equal to EI plus ER tan. There is no transmitted electric field, right, which means that the line, all right, the constant lines in z direction where the electric fields are looking as 0 can be thought of as a surface of a conductor itself. Okay. It is as though you have placed an ideal conductor at some location. So, electric field equal to 0 means that you do not have a potential gradient across that region, and you can always say that you have placed a conductor in that region, right. So, it is an imaginary plate. If you keep it there, the electric fields would have disappeared to 0. So, it also means that suppose I do place a second conductor, okay, and it will satisfy the boundary conditions that we have written originally. It will satisfy the expressions for the electric fields that we have written prior, all right. So, it will appear as though nothing has changed in the system except that you have placed an actual conductor on the left side. Okay. So, you could always take a semi-infinite conductor, all right, and you can place it on the left side. It is an ideal conductor, and that would not change the expressions for the electric or the magnetic fields inside this region. Okay. So, one thing that we can start now looking at is what happens when you have multiple conductors coming into the picture. So, the schematic now would look like so, I have an ideal conductor on the right, an ideal conductor on the left side. On both of these surfaces the boundary conditions are satisfied, and you will notice that you have not perturbed the fields in any way. Okay. Now, what could the result be? Okay. We already saw from the previous class that you are not having an energy transfer along this horizontal direction, which was the case of you do not have transfer of energy into the conductor at all right. Also we notice that since you are launching the field in this manner, all right, goes, bounces off the interface and travels upwards. Suppose I placed a second conductor somewhere over here, this wave would travel further, nothing would be transmitted into the ideal conductor and it would get reflected back, all right. And you will notice that there will be some net travel in the positive x direction. Okay. So, you will be having some net travel in the positive x direction, which is consistent with what we have seen. In the x direction it was a travelling wave, all right, and in the z direction it was a standing wave pattern, all right. And since this is a travelling wave in the positive x direction, in this configuration if I placed a second plate on the left side, there would be complete reflection from that plate and there would still be a net travel in the positive x direction, exactly following the expressions that we have written before, right. The consequence of this is that the wave is going to be completely confined between these two plates. Okay. So, it is not going to be spreading everywhere, but the electromagnetic wave is going to be completely confined between these two plates, all right. And if the two plates are going to a large distance or the large x direction, the wave is also going to travel bouncing back and forth between these two plates and reaching another side. Another way of thought is, if you did launch a wave on one end of a parallel plate configuration, all right, you will notice the wave emerging out of this parallel plate configuration on the other side, all right, without diverging, without going out of this region at all, right. So, since this wave is completely being guided from a source to an end, all right, by merely using two parallel plates, such a configuration is known as a parallel plate waveguide. Okay. Okay. This is known as a parallel plate waveguide. So, one could also think of what else can you do with parallel plate waveguide other than having them straight. Well, because you are making these out of ideal conductors, there is no requirement on you to make it completely straight. For example, you could take this, curve it, all right, and make it go 90 degrees to the other side, and it will bounce back and forth and it will find its way out on the other side, right. So, you can take the wave and you can guide it in the way you want, all right. There are some extreme conditions that you may have to think about later, but for now, if you had these two parallel plates, the electromagnetic wave is going to be between them, all right, and the net direction of travel is going to be in this direction unless you bend the plates in some way. For example, if you bend the plates like this and then back, then you will be starting to get the wave going in the horizontal direction, etc. So, you can play with the way the wave will actually travel and the net energy is going from one side to the other end of the parallel plate configuration. So, this is the premise of what is known as a parallel plate waveguide. An equivalent in optics is you just consider that you have two mirrors, perfectly plane mirrors, all right, positioned parallel with each other. You will just shine a beam of laser on one side, it is going to bounce back and forth and go to the other side, all right. That is an analogy, right. It is not going to work in the same way, right, but it is just an analogy, right. Now, one of the things that we have to start looking at is what is the difference between directly shooting an electromagnetic beam from one side to the other side and actually doing this kind of a configuration, right. Well, the first thing that I notice is the propagation is not directly in between these two plates, that is, you do not have the energy transfer directly going like this, but instead the wave is undergoing multiple reflections, all right, and then there is an effective movement in the x direction. Now, if you have a casual observer placed outside of this waveguide configuration, the observer will notice that a plane wave has been launched at some instant of time and they note down that time, all right. Then they note down the instant at which the wave emerges out of this parallel plate configuration on the other side. Okay. They can measure the length of this parallel plate configuration, all right. Then they try to find out the distance or the length, all right, length divided by the time it took for the wave to come from one side to the other side, and they will notice that even though in between you had air, for an observer who is outside, all right, the velocity is actually small, okay, compare to homogeneous air, right. So, this is the first thing that we have to realize. The consequence is that you are going to have propagation that is slower than in a homogeneous dielectric medium, because it does not travel, it does not follow the path of the least distance between point A and point B. It is bouncing multiple times and it is reaching on the other side. So, you can call these kinds of configurations as delays, all right. So, you are taking a signal and you are passing it through this configuration at a specific angle. It will be delayed by so much time when it reaches the other side. So, in a simple scenario, all right, a waveguide can be used as a delay element. Why would one use delay element is, there are a lot of factors involved. For example, if you are having some two signals and you want to make a logical operation out of them and or not and or etc., all right, you may get one signal on one of the pins, input pins first, and you want to wait to make the decision after the second signal also arrives at the second pin, which means that you want to delay one signal, the first, the signal with respect to the other, so that both of them are arriving at the same time, etc. So, the purpose of the delay, there are numerous purposes for which people can use, but compared to a homogeneous medium, if this is vacuum or air, compared to the scenario where you do not have these two plates, for an observer from outside this system, the velocity in this will appear to be smaller than the velocity in homogeneous vacuum. Okay. This is the first thing, right. So, you cannot have waveguide like this, right, which will give you velocity equal to that of bulk homogeneous medium, right. This is the first thing that we have to notice. Right. The second thing is, immediately I have used an incident angle of theta I in the previous class to denote the angle of incidence. We already know that if theta I is going to be small, if theta I is going to be large, right. If theta I is going to be 0 degrees, which means that I am not having an effective movement going in the positive x direction at all, I am going to be having the wave merely bouncing between these two plates and there is going to be no travel. For an observer who is outside, all right, it means that there is an infinite delay, okay, or the velocity has become 0. Okay. If you change the angle, if you keep increasing the angle, for an observer outside, the velocity will keep increasing, all right. So, this means that in this case the velocity is not fixed, the velocity does depend upon the angle of initial launch into the system, and for an observer who is outside, depending upon the angle of launch, the velocity is going to be different. That means that there is a possibility of constructing variable time delay by merely changing the angle of launch. Okay. So, it is not a fixed delay, it could be a variable delay, right. It could go all the way from infinite delay to almost no delay compared to a homogeneous medium if you launch it straight in between these two plates, right. So, it is a delay element, all right, but it is a variable delay element if you do have control over the angle of launch of the electromagnetic wave. Okay. Now, one could also think about this in a connected way, right. So, let us say that as an engineer you will construct this configuration first and then you will start doing some analysis. Okay. So, you can say that you can construct a parallel plate with distance between the plates being say denoted by d, because it looks like a parallel plate capacitor, right. So, distance between the capacitor we usually call it with the letter d. So, you can just use d, right. Okay. Now, is it true that at all angles, Okay, is it true that at all angles the boundary conditions will be satisfied just like what we were talking now, right? We are saying that as the angle changes, okay, as the angle changes, there will be no perturbation whatsoever smoothly. Is it really true? Okay. So, the condition is we are looking for zeros of the electric field. As long as you do not alter the zeros of the electric field and you have placed the plate exactly at the zeros of the electric field, what we are arguing is correct. Okay. But the condition for zeros of the electric field was cos theta is equal to m lambda 1 by 2d. This is what we had written. Right. Z is of course the distance between the two plates which has been replaced to d, all right, and cos theta I is m lambda 1 divided by 2d. This condition has to be satisfied for you to have zeros located in the manner in which we derived before, right, which means that we have to look at this a little bit more carefully. Is there specific angles at which you can launch? The answer seems to be so, right. Cos theta I is m lambda 1 divided by 2d. So, let us take that rosy picture and repaint it again, all right. Originally we said that we have a parallel plate, it will be a source of a delay. It is a variable source of delay depending upon the angle of launch, but it is not going to be a smooth variation of delay by no means, all right, because m is an integer, okay, m is an integer, all right, and we know that cos theta I cannot be greater than 1. So, this has to be less than or equal to 1, right, the magnitude at least, right. The absolute has to be less than or equal to 1. So, there are constraints in the way you launch the electromagnetic wave. You cannot take any parallel plate configuration and just say that you will launch the wave and you will get a very perfectly controlled delayed version on the other side. Looks like there is some constraint on the angle. Okay. Now, we have to look at this even more closely. Is there a constraint on the resolution of the angle, or is there a constraint on something else, all right. All we are trying to say is this cos theta I magnitude has to be less than or equal to 1, okay, which means that already we are seeing that there are a finite number of angles for a given separation, because you cannot keep on increasing m to 3, 4, 5, 6. Suppose d is given, all right, lambda 1 is given, okay. You can choose values of m which will make cos theta I less than or equal to 1, modulus of cos theta I less than or equal to 1. You cannot simply choose m equal to 10,000, 20,000, etc., all right, and the m lambda 1 divided by 2d, the modulus becomes greater than 1. So, this places some constraints. You cannot have any choice of m, you can have only finite choices of m for a given constructed parallel plate waveguide with separation d. Okay. Since there is only integer values of m being assumed over here, there are very limited angles at which you can launch and actually not perturb the system and get an outcome outside. Okay. So, it is a delay, but it has constraints. You cannot launch at any angle and expect the electromagnetic wave to arrive at any any configuration. For a given configuration, there are finite number of angles. As long as this angle satisfies the condition that the absolute value of cos theta is less than or equal to 1 or m lambda 1 by 2d is less than or equal to 1, only then you are going to be having some waveguide like properties. Okay. So, first of all, we notice that the velocity is smaller. Second, we notice that it can act as a delay element. Third, it is not a fully controllable delay element. It has got its quirks. There are only finite number of angles at which you can launch. Okay. What else? Okay. Let us look at the total field expression once again. Okay. So, I am going to take the total field expression once again. Okay. Going to take the total field expression, and all I am going to do is substitute for cos theta I. Okay. I know that cos theta I, the way we have written here, is m lambda 1 divided by 2d. All right. Of course, the choice of m has to be guided by the principle that modulus of cos theta is less than or equal to 1, but it is m lambda 1 divided by 2d. Right. So, I want to make some substitutions for cos theta I as m lambda 1 by 2d, sin theta I as square root of 1 minus cos theta square. All right. So, I just want to make that substitution in the total field expression. So, I can just say that this is minus 2j E I naught sin. So, I have beta 1 z m lambda 1 by 2d times e to the minus j beta 1 x square root of 1 minus m lambda 1 by 2d square. Okay. So, I have just taken some constraint that I have with respect to cos theta I. There is an equality there, m lambda 1 by 2d, and the choice of m of course is guided by the fact that mod cos theta I has to be less than or equal to 1, but suppose I did make that choice, the total fields has to follow this particular relationship. All right. Now, there are a lot of things happening over here. First of all, we know that this is an expression which tells you that there is a propagating wave in x, standing wave in the z direction. Right. On top of that, the pattern depends upon the position, that is the distance between the two plates d and the number m that you can choose. Okay. So, there are too many parameters happening over here, but let us just have a look at the x direction first. I have e to the minus j beta 1 x square root 1 minus m lambda 1 by 2d square. Let us look at this first. Okay. Suppose I were to create a new medium to understand this, right. Let us say that by taking a original medium to be beta 1. So, I say that vacuum or air had an electromagnetic wave launched into it of wavelength lambda 1, all right, and the beta 1 in that medium is 2 pi divided by lambda 1 in that medium. So, since it is vacuum, there is no change over there, 2 pi divided by lambda 1, right. But when I am putting two plates, all right, it looks like a phase constant that is different from beta 1. Right. It is beta 1 multiplied by x square root 1 minus m lambda 1 by 2d square. Right. So, previously we would have just had e to the minus j beta 1 x, but now you are having some square root 1 minus m lambda 1 by 2d square. So, this parameter is coming into the picture because you have added some two plates with a distance d between them, all right, and your choice of m is such that mod cos theta I is less than 1. So, we can always say that you can create what is known as a beta w. W is just for a waveguide. Okay. It is a waveguide, it has the same homogeneous medium beta 1, but in between two plates separated by a distance d. It seems to have a different phase constant if you define beta w to look like beta 1 square root 1 minus m lambda 1 by 2d square. Okay. If I do this, then I can write down the exponential as e to the minus j beta w x. Right. It looks like a homogeneous medium with a phase constant of beta w. Right. So, there are a few things once again that we need to look into. Okay. The first of all, the propagation constant is different from the homogeneous bulk medium. It is definitely different. Beta W is not equal to beta 1. It could be if you choose m is equal to 0. Okay. It could be if m is equal to 0 or d is equal to infinity. That is, the second plate is not even placed, all right. So, it reduces to a single plate configuration, right. Okay. Now, what would this mean? Right? Okay. So, by placing two plates in a homogeneous medium, a lot of things changes. First of all, the effective velocity has changed, phase constant has changed. If the phase constant has changed, we know the formula for phase constant, which means that the effective wavelength inside of this configuration has also changed, all right. The angle of launch, previously you had no restriction, you could launch wherever you want, all right. By putting the second plate, in order to satisfy the boundary conditions, you have to launch it at certain angles only for you to get a travelling wave in the x direction and have all the boundary conditions to be satisfied in the z direction, right. So, a lot of restrictions have come into the place, right. But what does all this mean? This means that let us take the parallel plate configuration that we have drawn, okay, and look at it a little bit more closely. Okay. Suppose my choice is m equal to 0, I just want to draw the total fields, okay. I just want to draw the total fields, and what I want to do is I want to go from one plate to another plate and I want to draw the relative total fields. That is, I want to say on the left side it is an interface, it is going to be 0, on the right side it is going to be 0, in the middle what is going to be happening is what I want to make a plot out of. So, I can draw a line like this and I want to draw the magnitude of the or the amplitude of the total fields, right. So, for m equal to 0, right. So, you can go back to the expression for the total fields that we have written. M equal to 0, okay, would mean that the sign is equal to 0 and consequently you have no electric fields being present at all, okay. M equal to 0 is thus not a very viable option. There are no electric fields present inside the two conductors at all. So, if I were to draw this, right, I would be having just a flat line like this where this edge corresponds to 0. It has to satisfy the boundary condition. Boundary condition is that at the interface between the dielectric and the conductor you have 0 electric fields. In between it is governed by that expression for the total field, it is 0, okay. No electric fields for m equal to 0. So, there is a constraint, okay, first of all. Let us have a look at the same thing. Let us say m is equal to 1, okay. I go back to my expression, I plug in m equal to 1, all right. So, m equal to 1 will make this lambda 1 divided by 2d. So, I have beta 1 z times lambda 1 divided by 2d, right. Now, what I am trying to plot is with respect to the z direction what is happening to the electric field. So, I will keep all the other parameters constant, vary only the z to go from one plate to another plate, and I will try to plot what is going to be happening. I know that at the edges the fields are going to be 0. In between I can see that as z increases, right, there will be a pattern that is evolving, right, and this pattern is something that we have already seen without m, right. In the previous class when we tried to write a program and try to visualize the fields, we saw that there is a standing wave pattern, all right, in the z direction. The nodes are fixed with respect to z direction, you will clearly notice a standing wave pattern for the magnitude, right. So, here what you will end up seeing a electric field pattern like this. At the edges of the dielectric conductor interface, you will be having 0 fields corresponding to the boundary conditions. In the middle, you will be having a maximum, value of the electric field. Okay. Now, this gives some hope that there is going to be an electric field present within the medium, all right, and we also say that there is a maximum of the electric field present right in between the two conductors. So, the maximum of the electric field is present right at the center of the waveguide. Okay. So, we can say that let us now take a different scenario and up the value of m to 2, right. You go back to your total fields expression, take the program, keep all the things constant, right, and try to vary only z. Okay. You will notice that for m equal to 2, you will notice that your total electric field would vary like this. As you go from one plate to another plate, the electric field will go to a peak, then it will have a 0 crossing, then it will go to a negative peak, and then it will end on the other plate. If you wanted to plot the magnitude, then you would look like, you know, two lobes in the positive axis. But here I want to make an emphasis that it does change sign, right. So, m equal to 2 corresponds to this kind of a electric field profile. We notice that m equal to 0 had no peak, m equal to 1 had one peak, m equal to 2 had two peaks, right, one in the positive and one in the negative direction. So, also m equal to 2 is a case where the center of the waveguide has no electric field. Okay. So, we can also go one step further and say that the red color profile that we have drawn is symmetric about the center of the waveguide. That is, if I take the waveguide, fold it into a half like this, the profile is going to be symmetric, all right. Whereas, in the case of m equal to 2, if I were to fold it, it is not really symmetric because one is having a peak in the upward direction and the other one is having a peak in the opposite direction, right. So, we can also say that this m equal to 1 is a symmetric mode, okay, and m equal to 2 not a symmetric mode, an asymmetric mode, right. So, these are some observations that we can make. You can keep drawing for m equal to 3, m equal to 3 will have 3 half cycles of the sinusoid, m equal to 4 will have 4 half cycles of the sinusoid, etc. So, the m actually signifies how many half cycles of the sinusoid you have within the parallel plate configuration. M equal to 0 has 0 half cycles, m equal to 1 has 1 half cycle, m equal to 2 has 2 half cycles, right. Half cycles is a full wave, 2 half cycles is a full wave. So, it keeps going like this. So, the electric field can have these kinds of patterns. But what is interesting is that the change is not continuous. That is, you can have either m equal to 0, m equal to 1, m equal to 2, etc. You can have either the electric field having the red color profile or the green color profile, for example, in this case what we have drawn. It does not go systematically from one profile to another profile slowly. There is an abrupt change, either you have this or you have something else, all right. That is coming in because of the integer nature of m that we are considering over here, all right. So, this means that the E field profiles are kind of discrete, okay. This is not a continuous change from one profile to another profile, all right, and this is also a very important thing, right. Why do we need to know these shapes? Because initially in the beginning of the lecture we talked about the waveguide being present between a transmitter and a receiver, right. Suppose you did transmit, all right. Let us say that your receiver is going to be of a finite area compared to the waveguide, all right. Let us say that, just for the sake of argument, we will make the area to be less than that of the waveguide. Okay. Normally it is not so, normally the receiver will, the detector will be much larger than your waveguide, but just for the sake of argument, right. Let us say that I have a detector which is smaller in size, all right, and I want to be able to get the maximum information coming from the transmitter side. Then the question arises, should I position my detector, all right. Detector is something that will take the electromagnetic wave and convert it to electric current. Okay. Should I position it at the center of the waveguide? Should I position it at first quarter, second quarter? Should I position it, where should I position my detector to get the maximum information? That becomes a question, all right. What size should the detector be in order for me to get the maximum information? Of course, you have to be the entire length of the waveguide has to be covered, all right. So, a lot of things can happen if you want to take a detector that is smaller. When people do this, that also you need to know, when do people use tinier detectors in between the waveguide to get this. Suppose the experiment is to figure out the mode profile itself. These are known as modes, m equal to 0, m equal to 1, m equal to 2 are all known as modes. In order to know the profile of the modes, the only way to know it is if you use a tiny detector and you move it from one wall of the waveguide to the other wall while you are measuring the current. Okay. Then only you will notice that, oh, there is a maximum current at the center. So, this kind of a profile is a m equal to 1 profile, you can say, right. If you move the tiny detector going from one side to the other side and you measure a positive peak, a negative peak, or negative peak, I do not know how you will measure, but you will be measuring two half cycles clearly or 3 half cycles clearly. Those cases you can say the mode that it is having is corresponding to m equal to 2 or m equal to 3, etc. So, these are known as modes of a waveguide, all right, and there are no gradual changes between one profile to another profile, all right. So, now we have written beta w is beta 1 in that medium multiplied with 1 minus m lambda 1 by 2d square. Okay. So, you can say this is corresponding to the homogeneous medium as 2 pi by lambda 1. If you want to write it in terms of frequency, you can write this as 2 pi f1 by velocity in that medium. If you assume it to be vacuum, V1 will be replaced with C. Okay. Now, I am having square root of 1 minus something square. Again, the choice of m is limited. Okay. If I make m abruptly large, what will happen is I will end up with a square root of a negative number, all right, and then I will have j times something multiplied with beta 1, and I have already exponential minus j beta 1 something, that j will multiply with just this j, and from being a quantity that tells you that there is a travelling wave, it will look like an exponential decay. Okay. So, there are constraints on how you can choose m, how you can choose d, how you can choose theta, right. So, just looking at the term inside the square root, I can say that for beta w to not become imaginary, right, beta 1 has to be greater than equal to m pi by d. Just taking beta 1 minus beta 1 multiplied by m lambda 1 by 2d the whole square, right, to the root, and then we are saying that one term has to be greater than the other term. Square root has to be greater than equal to 0. So, right. Equivalently, you can also write this down in terms of wavelength, right. So, you can say that this is 2 pi divided by lambda 1 has to be greater than equal to m pi d, right, or lambda 1 is less than 2d by m. Now, there are so many constraints, right. Theta has to be chosen carefully, m has to be chosen carefully, d has to be chosen carefully. Now, lambda also has to be chosen really carefully. Lambda 1 has to be less than equal to 2d divided by m, all simply because in a homogeneous medium you just place two plates, right. If you did not do this, if you did not place it carefully, we notice that beta w will become imaginary and there will be an exponential decay of your wave. For the wave to travel from one side to the other side, you need to meet all these criteria, all right. So, this lambda 1 less than equal to 2d divided by m means that you have taken a waveguide, you have constructed a waveguide with the distance between the plates to be equal to d. You are considering a profile of the electric field corresponding to m, and you have to make sure that the lambda 1 is less than equal to 2d divided by m. So, there is an upper wavelength of the source that you can launch into a constructed configuration of a parallel plate waveguide, right. So, this is known as cutoff wavelength. The term cutoff wavelength is usually not very popular, right. The signal processing community usually they talk about frequencies. Okay. So, you can always convert this to frequency and say that where v1 is the velocity in the homogeneous medium, right. So, this becomes cutoff frequency. What does this mean? For a given choice of d, all right, enclosing a medium with velocity v1 for a choice of the electric field profile m, there exists a minimum frequency. Okay. Only above this minimum frequency you will not have exponential decay of your fields and the fields will survive, all right. Below that frequency the fields will not survive in this configuration, all right. What does this mean? This means that the waveguide is actually an element that in signal processing you would call it as high pass filter. Okay. So, you supply all frequencies, the waveguides will transmit only frequencies above this cutoff frequency, right. So, it is a high pass filter by nature. Okay. So, the equivalent of a high pass filter, the case of transmission line or in the case of optics is going to be a simple parallel plate waveguide, right. So, you will have frequencies above this cutoff value being transmitted. So, if you are aware of a system where you have multiple frequencies coming into the picture and you want to make sure that you get only frequencies above something, you want to say remove noise, etc., you could construct something like this and make sure that only the signal is going through. The assumption there is signal frequency is higher than your noise frequency, right, which is not always the case, but it is a general assumption you can make. Okay. So, now we see that by placing a second plate in that medium you have imposed too many restrictions. Well, the consequence is that you will have electromagnetic wave going from one side to the other side of this configuration. You can also bend twist to anything with this configuration, but it does have some constraints, and the constraints are you have to choose the frequency carefully, you have to choose the velocity, you have to choose the distance between the two plates carefully, you have to also choose the angle of launch carefully, you have to choose the profile of the electric field that you want, and all of them have to be chosen carefully, then you will get a transmission. And inherently the waveguide is going to be a high pass filter. Okay. So, we will stop here, we will continue in the next class about this.